Welcome to the 7th week of this course. In the last week, we studied about two different methods of estimation, that is method of moments and maximum likelihood estimators. In these two methods, we found out how can you estimate the population parameter, and we came up with a single point estimator for that. Now, in this week, it is important to see whether the estimators that you obtained by using those two methods, do they have certain property or not? And in order to do that, the simplest property that we are going to study in this week is unbiased estimation, which basically means that we are going to see whether the estimator that we obtained in the previous week were they unbiased or not. In addition to this, we are going to learn about expectation maximization algorithm, because we want to see how do we do the estimation in case some observations are missing. Now, let us start with your unbiased estimation. So, the point is that you have taken a sample and you have calculated an estimator based upon that, or a statistic you have calculated, and when you use it for estimating the population parameter, you have obtained an estimator for that. Now the question comes up, how can you be sure that it is good, or is it actually close to the true parameter or not? Because if it is not close to the true parameter, then the answer that you have obtained or the point estimate that you have obtained is going to be incorrect. For example, if you are interested to estimate the average income of people living in your city, and the actual value is suppose 35,000, and what your estimator is, suppose you took a sample and based upon that you came up with an estimator and you said that the average income of people living in your city is suppose say 70,000. It is nowhere close to the actual population parameter, or you can say the population income, average income of those people. So it is important that your estimator that you are obtaining, it should be close to the true parametric value. And that is why we have the concept of unbiased estimation. When you have a random sample x1, x2, xn, which is coming from a probability distribution f with the parameter theta, where theta takes value in the parametric space, then estimator t of x, where here if you can see that this is a function of the random sample, it is said to be unbiased for estimating this parametric function. Here, if it satisfies this criteria, that if you are taking expectation of this estimator, this is same as this estimate over here, g theta, right? So this is your function of the parameter. So you are not directly interested in theta, but rather some function of the parameter. Okay. So now what it is saying is that when you are taking samples again and again and you calculate your estimator, then on an average, it should give you the true parametric value. Okay, or you can think of it as the sampling distribution of this estimator should be centered around this population parameter, or you can say that this parametric function g theta. Now, if it is not same as g theta, sometimes it might be less than or greater than g theta, it means that there is certain sort of bias present in that. Because when it is equal to this, then only it is unbiased. And if it is suppose less than this or greater than this g theta, it means that it is not unbiased, it is biased. That is why we define this quantity b theta as the bias of this estimator. Now this b theta that you have over here, which is a function of your theta, that is the original parameter, this can be positive. If it is greater than 0 for every theta, then we say that you are overestimating the parametric function over here, g theta, because here you are adding certain quantity. You are not getting exactly g theta, but rather you are adding certain quantity to it, and then your expectation is same as that. It means that you are doing overestimation in that process. Likewise, if it is less than 0, it means that you are subtracting something from g theta. The original, had it been g theta, you would have said it is unbiased, but since it is less than g theta, you are subtracting something from that. You say that it is underestimating your parametric function. Okay. So to understand this, let us consider different examples. The first example over here says that if you have a Bernoulli random variable with parameter p, then p hat, which is 1 over n summation xi, is the MLE of this parameter. We have seen this last time also. Then we need to check whether the MLE that we obtained is an unbiased estimator of this parameter or not. The next question over here is that if xi's are normally distributed random variables with mean mu and variance sigma square, then what is the unbiased estimator for sigma square? So let us first answer these two and then we will move ahead. The first example says that if you are taking a random sample from Bernoulli distribution with parameter p, then in that case p hat, which is x bar, is going to be an unbiased estimator for p, which means that if I take expectation of p hat, I should get the population parameter. Okay, so this is what I want to show. To understand this, it is simple to see that if a random sample is coming from Bernoulli distribution, it means that expectation of each of these xi's would be same because they are IIDs, right? So x1, x2, xn, and what is the expectation of each of these? This is p, because this is Bernoulli. So if I have to take expectation of p hat, we are starting with the left hand side. This is same as expectation of 1 over n summation xi, where I goes from 1 to n. Now 1 over n can come outside because we know that if expectation of ax is there and a is some constant, so a is just same as a times expectation of x. Now 1 over n comes outside, you can take summation over here and expectation goes with xi's, and we have seen that each of the xi's has the same mean, that is p, and there are n such terms, so it would be 1 over n into n p, right? So n would cancel out and what you are left with is just p. So this is an unbiased estimator of your mean, of your population parameter, that is p. So sample mean, basically when you have the Bernoulli distribution, you are taking a sample from Bernoulli distribution. In that case, when you have the sample mean, then basically it is going to be the unbiased estimator. Basically means that it is going to have a very nice property of unbiasedness. Now let us move to the second example. The second example said that if you have a random sample coming from normal distribution with mean mu and variance sigma square, in that case, what should be the unbiased estimator for sigma square? See, if you can recall that whenever we are dealing with the variance, then chi-square distribution comes into picture, right? And also when we are dealing with mu, then, so in that case, normal distribution or t distribution would come. So here we are using chi-square, and we also know that sample variance would be coming here because sample variance would be related to the population variance, and we have also used an initial result that expectation of a square is sigma square. If you remember from your 4th week, that is sampling distribution chapter, in that we saw that expectation of sample variance is same as sigma square. So this is the same property of unbiasedness only, because you are taking expectation of this estimator and what you are getting over here is the population parameter. Okay. In addition to this result, we also studied one more property, that n minus 1 times s square over sigma square, it will follow chi-square with n minus 1 degrees of freedom. Okay. We also know that when you have a random variable x which is following chi-square with r degrees of freedom, then expectation of x is simply those degrees of freedom r only. Okay, so with this knowledge we are going to address, so first is this thing, second is this point, and the third point is this. Okay, so in this case, if I just start with the expectation of the sample variance, so let me multiply and divide it by this term, n minus 1 over sigma square into sigma square over n minus 1 s square. So this would be the same quantity. Now I can take outside sigma square over n minus 1 outside the expectation, and what you are left with is n minus 1 over sigma square into s square. And this quantity, if you look from the second point over here, expectation, and using this second and third, you know that expectation of this quantity is r. It means that for this it is following chi-square with n minus 1 degrees of freedom. So it means it would be n minus 1 also. So this is same as variance, right? So what you obtain is expectation of s square is same as your sigma square, that is, it is an unbiased estimator. So we proved this result initially in the sampling distribution, where we said that it can be a random sample from any population, and here we have specifically studied about the normal distribution. So now let us look at the third example, which says that if you have a random sample coming from Poisson distribution with parameter lambda, and we saw that the method of moment estimator in this case came out to be the sample mean. Now we are interested to check whether it is an unbiased estimator for lambda or not, and if it is, then is it a unique unbiased estimator, or there are more unbiased estimators to that. And finally, we are also interested to see what will be the unbiased estimator for the probability of no occurrence. So let us answer this. So coming to the third example, we know that x1, x2, xn is a random sample coming from Poisson distribution with parameter lambda. So in this case, what we are given is that lambda hat estimator was x bar, and we have to check whether this is an unbiased one or not. So let us simply do it. Expectation of lambda hat, which is same as expectation of x bar, so 1 over n expectation of summation xi's okay. So here it would be n times, because each xi's would have the expectation as lambda only for I 1 to n, right? So it means this would be n lambda, and n would cancel out, it would be simply lambda. The next example could be, so the next part over here was to see whether x bar over here, this is a unique unbiased estimator or not. So in this case, what we will do, we will take expectation. So the next part over here is to see whether this is a unique estimator or there exists some more unbiased estimators for lambda. So here it is very easy to see that if I take even expectation of x1, or if I take expectation of x2 and so on up till xn, each of them has the same expectation, that is lambda, because they are all coming from Poisson distribution. So it means that each of these xi's, these are also unbiased estimators for us. In addition, if I take some other one, that is expectation, suppose if I take 2x1 plus x2 plus x3 and I divide it by suppose 4, then what will happen? I can take expectation inside, expectation of x1 plus expectation of x2 plus expectation of x3 whole divided by 4. What you get is each of these is lambda, so it will be 4 lambda over 4, which basically means it is lambda. So again, this is an unbiased estimator for us. Or if I take the sample variance also, then also it will give you the population variance, because in this case for Poisson distribution, sample mean and variance both are same, right? So in variance would also be lambda. So there's a pool of unbiased estimators in this case. So we do not have just a single unbiased estimator. In fact, we have numerous unbiased estimator. So here we see that sample mean is not just a unique unbiased estimator for lambda, rather there are various other unbiased estimators. And since here our course is only an introduction to statistics, we are not going into more detail that how do you find a unique one from that, and that you may study in your statistical inference course. And we find out ultimately that obviously there are other properties in addition to unbiasedness. So basically we move on to the point that we are interested to find out that unbiased estimator which has a uniform minimum variance. So we refer to it as UMVV, that is uniform minimum variance unbiased estimator. And since those things are not a part of this course, we are just understanding the concept of unbiased estimation. Now let us see what is the unbiased estimator for this quantity. Probability that x is equal to 0 is same as e power minus lambda. So how do we get this? I have explained this earlier also. Since this is a Poisson random variable, so it would have the PMF e power minus lambda, lambda over lambda raised to power x, and x takes value 0, 1, 2 and so on. So if x is the number of times an event occurs, so it can be 0, it means that none of the events have occurred, 1, 2 and so on. So in this case, if it is 0, it means that no event has occurred, and we are interested to estimate this probability, and it is of interest in many situations, because if you know this probability, the shop owner or the cafe owner, they can employ that person to some other task, or maybe they can just shut down the cafe during that particular period. Okay, so that is why this is important. And in order to estimate this, we have a very simple estimator, that is Ix. We define this indicator function as 1 if it takes value 0 and it is 0 otherwise. Okay, so now if I take expectation of this indicator function, so we know that expectation formula is that you multiply the corresponding values with their corresponding probabilities and you add it up. Summation x into probability of x. So 1 into probability that x is equal to 0 plus 0 times probability that x is not equal to 0. So here it is same as probability that x is equal to 0, because the second term would be eventually 0, and this is same as e power minus lambda. So what you see that I took expectation from here, expectation of I, that is indicator function, and finally we obtained e raised to power minus lambda. Okay, so you have been able to find out an unbiased estimator for this quantity. So till now what we have been doing is that we found out the estimators from the previous lecture, and that same estimators we were considering over here, and now we were trying to see whether they were unbiased or not. Now the question comes up is that if you have to find out an unbiased estimator from scratch, you do not know that what is an unbiased estimator or what is an estimator beforehand. In that case, what we do is that we directly solve this equation, expectation of t of x, that is g theta, for every theta taking value in the parameter space. To understand this, let us consider an example of truncated Poisson random variable. So here you see that it is a truncated one because first of all x is starting from 1 as opposed to the usual Poisson distribution which starts taking value from 0, and also the PMF is somewhat different in this case. And this is important, and this distribution basically can arise in situations where you know that 0 is not going to occur. So basically the probability of an event not happening at all is 0, right? So you know that it is not going to happen, so you have basically truncated it, and we have considered the new form of this PMF. And in this case, we are interested to see what will be an unbiased estimator for this. So let us consider this example over here. We are given truncated Poisson with PMF probability that x is equal to x is 1 over e raised to power lambda minus 1 into lambda power x over x factorial, where x takes value 1, 2 and so on. Now what we have to do is we have to find an unbiased estimator for lambda, And for that, let us start from expectation of t of x. So we basically don't know what is an estimator, and we are going to start from scratch. So for this expectation of any quantity, we know that in the discrete case, it will start from 1 to infinity, and we write the function that t of x, and we multiply it with the corresponding PMF. So that is e power lambda minus 1 into lambda power x over x factorial. This is same as lambda. Alright. Now if you simplify this, it is same as expectation of t. This summation tx, we can keep the x terms over here, and we can take lambda into e power lambda minus 1 to the right hand side. This is same as this. Now it is equal to saying, now if you expand this, this is t raised to t1 lambda over 1 factorial plus t2. So we are basically substituting the values of x over here. So lambda square over 2 factorial and so on. And on the right hand side, we will have lambda, and e power lambda minus 1 will be what? 1. If you expand this, 1 would cancel out, and the first term that you have will be lambda plus lambda square by 2 factorial and so on. This. Now we know that these are the power series, and they can be identical in an open interval if and only if all their coefficients are matching. So if you match the coefficient for lambda, then you can see that on the right hand side you do not have a lambda term. So it basically shows that t of 1 is basically 0 in this case. Now if you look at t2, what is happening? If you look at the, so for lambda square it would be t2 over 2 factorial, okay, and you are comparing it with, on the right hand side you would have lambda square, that is 1, lambda square is there, so 1, so this implies t2 is basically your 2 factorial. Next, if you compare the coefficient of lambda cube, then it would be t3 over 3 factorial, and on the right hand side you would have 1 over 2 factorial, and if you solve this, what you get is t3 would be 3 factorial by 2 factorial, which basically means it would be just 3. Okay, so this is same as 2 only, and so on, it will keep on going, right? And if I go up for this up till suppose say rth term, so it would be tr would be r factorial over r minus 1 factorial, which basically is simply r. Okay, so this is your estimator now, and if you look at, you just summarize it, so t of x, it is taking value, so when x is your 1, if x is 1, then this estimator takes value 0, and if x is 2, 3 and so on, it is taking the value x itself, because when it is t2, when x is 2, it is giving you 2, it is 3, you are getting 3, and for r you are getting r, right? So this is your unbiased estimator. So you have obtained this unbiased estimator using the form of directly solving the equation, right? You started with expectation of tx, and here you have just used the concept of expectation, okay, and we have just simplified it and obtained the unbiased estimator for the parameter lambda. Next, what we see over here is that unbiased estimators, there are many unbiased estimators, right? So if you are given any unbiased estimator which is not based upon the MLE, then there would exist another unbiased estimator which would be based on the MLE, and that estimator would be a better unbiased estimator. Okay, so if you have to compare two unbiased estimators, and then the one which is based on MLE would be a better one. Okay, so there are results which further explain why is this so. So that will be covered in your statistical inference course, and it is not a part of the course at present. So now what we see is that there are many unbiased estimators. So how to choose the one which is better? The simplest idea is that if you are given two unbiased estimators and one unbiased estimator is based on the MLE and the other one is not based upon MLE and is entirely different from that, then the one that is based upon the MLE would be a better unbiased estimator. Okay, so whenever you have to find out a sensible unbiased estimator for your estimate G theta, you typically start with the MLE of that. Once you start with the MLE of this estimate, then finally whatever unbiased estimator you get, it would be a better one. To understand this, let us consider two examples over here. The first example says that if you have a random sample coming from Poisson distribution with parameter theta, and your estimate is this same quantity that we have studied earlier also, e raised to the power minus theta, then you have to find out an unbiased estimator for this. Okay. Next can be a random sample which is coming from uniform 0 theta, and the estimate in this case is theta raised to power r for some positive integer r. You have to find out the unbiased estimator for this. So if you see that for e raised to the power minus theta, here in this case we are focusing on the general Poisson distribution as opposed to the previous one where we studied your a truncated Poisson distribution. So let us answer these two. So our example, first, when you are dealing with the unbiased estimators based on MLE, says that if you have a random sample which is coming from Poisson distribution with parameter theta, and your estimate in this case is e raised to the power minus theta. Now if you remember the third example that we studied today, and we found out that x bar is an unbiased estimator for theta, right, or lambda. There we considered the parameter as lambda, so it's same thing. Expectation of x bar is theta, and by the invariance property we know that, and this was the MLE also for us, x bar. So we know that if x bar is the MLE of theta, then e raised to the power minus x bar would be the MLE of e raised to the power minus theta because of the invariance property that we have studied earlier. Okay, so now it says, our result says that if your unbiased estimator is based upon the MLE, then it is going to be a better one. So let us start with this. Here we have x bar. X bar is basically what? 1 over n summation xi, right? Now if I denote summation xi with some other variable, suppose z, then x bar would be z by n, right? Where if you just look at z, z is summation xi, z is following Poisson distribution again, but the parameter would be n theta. Why? Because you are having xi's. If xi's are following Poisson distribution, then if you add them up, if they are independent and if you add them, it would be Poisson because there are n such terms. So it would be n theta. And the corresponding PMF would be what? E power minus n theta raised to the power x, or maybe here you can say it as j suppose, and here it would be j factorial, right? So probability, this is the probability that z is equal to j, right? Because z is following Poisson with parameter n theta. Now with this knowledge, let us start with your result. Let us start with expectation of t, function of the sample mean. Let us consider over here, because t of x bar e power minus theta, this is what our area of interest is. Now what is t? X bar is what? We have defined it as z by n. So let us keep that, e power minus theta. Now we are talking about the PMF, so we can just simply write summation. So summation can go from 0, j is going from 0 to infinity. It would be t. Instead of z, we can write j over n. And what is the PMF in this case? We have just now seen that it would be e power minus n theta power j over j factorial, which is same as e power minus theta. Okay. Now you can see that Here e to the power minus n theta, this term basically can be taken to the right hand side. So what you are left with, summation j 0 to infinity t jn n theta, so n to the power j over j factorial theta to power j, and if it goes to the right hand side, here it would be e to the power n minus 1 theta. Okay, this again further, you know that the expansion for this could be, this is same as summation j is equal to 0 to infinity. In this case, what it will be, n minus 1 times j or theta raised to power j over j factorial for every theta greater than 0, right? So here also you have theta j over j factorial, and on this side also, so we can just simply compare the terms on both the sides. What you will get is t j n, this is same as n minus 1 times j over n raised to the power j. So if you simplify this, this is 1 minus 1 over n raised to the power j. And what is j? J we used for z basically, right? J was used for z, and z is basically n x bar, because that is summation xi, right? So we can write j by n is basically x bar, t of x bar. The estimator is 1 minus 1 over n times n x bar. So this is a better unbiased estimator for your parameter e raised to power minus theta. If you remember in an example earlier, what we obtained, I can just go above and show it to you, that here when we had e to the power minus lambda, what was our unbiased estimator? It came out as an indicator function, right? And instead of that, it says that if I just consider this one, which is based upon the sample mean, then this is going to be a better unbiased estimator because it is based upon MLE. And also that estimator indicator function is not a good one because it is just taking two values on the ends, right, 0 and 1, and the parameter, that parametric function itself is not defined on that. So this was the first example. Now let us consider the second one. So the second example says that if you have a random sample from uniform 0 theta, x1, x2, xn is coming from uniform 0 theta, then in that case we have to find the estimate is basically theta raised to power r, and you have to find an unbiased estimator for this. If you can recall, for uniform distribution, the MLE was x ordered n, that is the largest order statistic. So it means that if you have the invariance property, then ideally x ordered n raised to power n is an MLE of theta raised to the power r, right? It means our unbiased estimator should be based upon this MLE. So if I take expectation of x ordered n raised to the power r, if I take this expectation, it would be from 0 to theta, because x uniform distribution, it is defined from 0 to theta, x raised to the power r, and you have the PDF of x ordered n. Now it means that you need to find out this quantity, that is the PDF for order statistic, the largest order statistic. The first thing that we know over here is f of x. So the density is 1 over theta, right, where x takes value between 0 and theta. The second thing what you can find from here, the distribution function is x over theta, right? So now I have to find out the distribution function for the largest order statistic based upon these two, because if I know the distribution function, I can differentiate it to find out the PDF, that is this quantity that we are interested in. Now What is the distribution function? By definition, it says that it should be x ordered n should be less than x. Here, if in the maximum quantity is less than something, it means that rest of the random variables also would be less than that, which basically means that each of these order statistics, the smallest one would also be less than that, the second one also would be less than that, and so on. You can keep on going, and the nth one would also be less than that, right? Now these are identically distributed, so you can basically say that probability that x ordered 1 is less than equal to x, I can raise it to the power n, right? Because all of these are identically and independently distributed. So if I have to write the distribution function, so if x is less than 0, this quantity would be 0. If it lies between 0 to theta, then in this case, what will happen? It will be this quantity. And what is this? We have seen that for any x, it is x by theta, so it would be raised to the power n. So x by theta raised to the power n from here. Okay. And finally, what you have is 1 if x is greater than equal to theta. So this is the distribution function that you have obtained. Now, the fourth thing can be, if I differentiate it, I would get the PDF corresponding to this. So what it will be? N x raised to power n minus 1 over theta raised to power n, right? So finally, we have obtained the PDF of the order statistic, that is the nth order statistics, the largest order statistic. So now let us reconsider this. Okay, so consider star. So we had 0 to theta x to the power r into n x to power n minus 1 theta raised to power n over dx. So this one would be n over theta to the power n, and here you are integrating x raised to power r plus n minus 1 dx from 0 to theta. If you solve this, what will you get? X raised to the power. So let me just write x raised to the power r plus n over r plus n from 0 to theta. So it would be n over n plus r, right? You substitute the value of theta, so it would be theta raised to the power n plus r over theta raised to the, so here it is n also, it would cancel out. So what you are left with is n over n plus r times theta raised to the power r. So what you obtain finally is that expectation of largest order statistic raised to the power r is same as n over n plus r raised into theta raised to power r. Your interest was in theta raised to power r. If I have to find out an unbiased estimator, so this is a constant for us, so we can just simply take it inside the expectation and it won't affect. So n plus r over n times x ordered n raised to the power r. This is going to be an unbiased estimator for your theta raised to power r, right? So this is basically your unbiased estimator. Okay, so you can see that this is based upon your MLE, and this is going to be a better unbiased estimator for us. So this basically completes your concept of unbiased estimation.